So today, what we're going to do is we're going to talk about fluids. And fluids are the beginning of the third major part of material for this semester. Now, we're familiar with position, mass, time. Position becomes area. Area can become volume. And with position and mass, we get velocity and acceleration. And we start getting other things where if we do mass times acceleration, we get force. And one of the things, if we do force times distance, we get work or energy. And we start seeing that when we mix together these variables and mix these ideas together, we come up with new ones. And we're all familiar with, and we talked about this last time, rho or volume density. And with volume density, rho, that's merely mass divided by volume. And the typical, in 213, the accepted densities that we'll be dealing with are in kilograms per cubic meter. What you all typically know in biology and chemistry and stuff like that is grams per cubic centimeter or grams per milliliter. And those are acceptable too. Probably one of the things that is a very acceptable question during tests are, well, what unit do you want this in? Kilograms per cubic meter or grams per milliliter? And I'll give it to you if it's not listed already. And the universal density that you all should just have a feel for is the density of water, which is 1,000 kilograms per cubic meter. So if you have a cubic meter of water, you have 1,000 kilograms of that stuff. Wood tends to be about, I don't know, 700, 800, depending on the material. Mercury has like a density of 13,000. I'm not really concerned about memorizing all these bizarre densities, mostly because I have this thing called a book and I just look it up. On the test, you'll either be looking for the densities or I'll give it to you. I have no problem with that. A material that I've created, and you will see this on a regular basis, is something called Rebellium. I guess I could get the trademark for it. Rebellium is a fictitious element. It's not real. I was amused one time when a student came in and said that the TA told them to just look it up on Wikipedia, they could find it there. No. Rebellium is me being lazy and going, I need a material of this density, let's go with it. Is it a liquid? Is it a gas at room temperature? Or is it a solid? Yes, it's whatever I want it to be. So with Rebellium, it's just some fictitious element. We'll be using it on a regular basis. As an example, let's say we had 500 kilograms of Rebellium, and its volume is equal to 0.1 cubic meter. Its density would just be mass over volume, and 500 divided by 0.1, 5,000 kilograms per cubic meter. And that's a very dense density. The mercuries and the leads are closer to 2,000 kilograms per cubic meter. This is really dense. And so that's a simple example. This equation right here, become very familiar with it and be very capable of solving for mass and solving for volume. And why is that? Because in many fluids problems, rho equaling mass over volume is like a Swiss Army knife. A very capable tool that when you have an unknown that's either density, mass, or volume, so many times the solution is to take this equation and substitute out whatever you don't like or whatever is unknown. So we have density, and there is, like as I said on Tuesday, sigma, which is mass over area, and that's surface mass density. And then there is lambda, which is more widely used than sigma, which is mass over length, and that is linear mass density. So we talked about those on Thursday, and so now we're going to start building on mostly rho. And an idea that we need to come up with or put forth is the idea of pressure. And pressure is force divided by area. Pressure, when you really, and what freaked me out as a kid is that you always see those movies of space stations and they open the door and it's space outside, and what happens? All the air just gets sucked out. And if you were to step outside and you looked up, it's just nothing between you and space. Why isn't the air just sucked off the planet Earth and just dispersed? Well, it's mostly because of gravity. Gravity is holding in those particles. And when you think about you just standing there, there is a whole column of air above you. And it's a lot like, you can think of another analogy is like you're oh my goodness, I was a high school senior. I got invited by my mother to visit her kindergarten class. Kindergartners just love, they're little devious little things. 1 or 2, you can throw a beat down on them and be fine. But when 25 of them get into their heads that you're it, 25 little 40-pound bodies just flinging themselves on top of you, that causes issues. And when one person is on top of you, it's okay. It's just a kindergartner. When there's 8 on top of you, now you're starting to feel a little bit squished. So what really is happening is that the collective force of all those kids on top of you is pushing down directly upon you. And this pressure is force divided by area. And then one of the things that tends to get the point across, since she has the very nice white shoes, I'll go after her. So if I took my foot, I'm not going to touch your nails. Her on the other hand. So if I took my foot and I just went boom right down on it, that hurt. I applied a force on a particular area of your shoe. Now let's move down here. Now if I had one, I'd actually bring it out. If I had an iron spike and I put it right down on top of your foot, and then I pushed down on it with the same force that I did to her foot, would that hurt more? Yeah, why? Smaller area. When I hit her foot, it was just the bottom of my shoe. When I hit the nail had that point right at the end, so it was the same amount of force over a smaller area. Smaller amount of area, greater pressure. Greater pressure, like right now, we're under a pressure of 1 atmosphere, just standard Earth atmosphere, and we're fine with that. But if the atmosphere got up to like 5,000 times Earth's atmosphere, we'd start feeling it, a little bit more crushed. And you can do increased pressure one of 2 ways. Increase the force or decrease the area, one of the 2. So this is...
I wasn't really going to hurt your foot. You looked all sad.
So with stuff like this, and this, once again, it brings up the idea of directly proportional indirectly proportional pressure and force are directly proportional. If you increase force, you increase pressure. They're directly related. Indirectly proportional is a lot like pressure and area. If you increase area, you decrease pressure. Also, you could say that force and area are indirectly proportional to each other. Can you say that? No. Why? Why can you not say that? Because, let's study this for just a moment. The best way to tell if something is indirectly or directly proportional is to get one variable on one side and the other one on the other. So pressure times area is equal to force. So if A goes up and P is constant, F goes up as well. So A is directly proportional to force. So we figured out the relationships. Pressure and force, area and force, they're directly proportional. Area and pressure are indirectly proportional. Now, let's get some units. Pressure, which is force divided by area. Force is in newtons, area is in square meters. So the unit of pressure is Newton per square meter. Not newtons per cubic meter, not kilograms per meter squared, newtons per square meter. The average, or the total force over the total area, gives you a distributed force over distributed area, or newtons per meter squared. Just like you have, yes? We're about to do that. So with newtons, newtons is a kilogram meter per second squared. So pressure will be kilograms meters second squared, then 1 over meter squared. So you could write this out as kilograms second squared meters. But that's not quite catchy. That's a little bit more on the confusing side. The units of pressure that we deal with on a more regular basis is the acceptable kilograms, or I'm sorry, newtons per meter squared. That's the one that we typically use, or one of 3 that we typically use. Yes?
On the other page where you said A is direct proportional to force, if A, or if area and pressure are indirectly proportional, then how would A increase and be so constant?
Well, what we're doing is we're declaring, in this particular case, I'm saying if I only allow area and force to change, then if area goes up, F has to go up if I set P as constant. In the earlier ones, I said, well, if I kept area constant, if area was constant and I only allowed pressure and force to change, an increase in force would cause an increase in pressure. In this particular case, I said constant F. So an increase in area would decrease pressure if you set up the experiment to say force was constant. So
See how, like we say, P equals newtons over U squared is the same pressure?
well, what I did is I substituted, well, what's a Newton? A kilogram per meter, kilogram meter per second. So if I took pressure, a Newton is a kilogram meter per second, and an inverse meter squared is 1 over meter squared. One of those meters cancels and I'm left with this. So it's just a little bit of unit play. The real way of describing the units for pressure, 1 Newton per meter squared is a Pascal. A Pascal is the unit of pressure that we typically use, though I tend to use this most often. Another way that we typically describe pressure is the pressure of the atmosphere, and 1 atmosphere of pressure is equal to 1.013 times 10 to the 5th newtons per meter squared, or you could say pascals, either one. And that would be fine. An atmosphere is a lot like a G of acceleration and acceleration of standard Earth gravity. A Pascal, or an atmosphere is 1 atmosphere of pressure, that pressure of the Earth's atmosphere at sea level. All right, so let's do some examples. Now, this, everybody's going, do I have to memorize 1.013 times 10 to the fifth? No, that will be on the test in the equation section. How did I memorize it? I didn't want to memorize it. But when you say 1 atmosphere is equal to 1.013 times 10 to the fifth newtons per meter squared, 50,000 times, you don't have to intentionally learn it. It just permeates your brain and sits in there, and then you just can't get rid of it. You have, let's say you have 3 cubic meters of water in a cylinder, a massless cylinder. Let's only worry about the water itself. The height of the cylinder is 2 meters high. What is the pressure of the cylinder What's the pressure of the cylinder on the floor if you have 3 cubic meters of water in a cylinder? Now, before we start talking about this problem, I have to warning is so strong a word. Basic volumes and surface areas will not be given in the problem section. And what's a basic volume or surface area? Well, if you don't know what a circumference is by now, we've got issues. The volume of a sphere, 4/3 pi r cubed. Volume of a cylinder is pi r squared h. Volume of a cube, or, well, that's L cubed. If we had surface areas, volume of, or a surface area of a sphere, 4 pi r squared. Cylinder, 2 pi r squared plus 2 pi r h. Cube, 6 L squared. The basic shapes that we cover in the problem set is your responsibility to learn. And why do I think about that? Or why do I consider it something that I won't give on the test? You're a college-age student. Basic geometric shapes should be just known to you because you have a 3-pound gland between your ears. There was one particular summer, it was the last summer that I gave these equations on the test because the students begged for me to put it on. And I was like, fine, I'm gonna go to my doctor, and it's called the Helmhout rule because my doctor is Dr. Helmhout in town. And I said, I'm gonna go to her, and if she can answer one simple geometric question, this is permanently eliminated from the test in terms of me giving it to you. And they said, great, as long as we get our equations, we're fine with it. So I went to my doctor and I said, I have a question. She goes, you can ask me anything. And I said, fine, what's the volume of a cylinder? And she went, pi r squared h? Now granted, she did answer it in the form of a question, but she did get it right. So if a doctor who's been out of med school for 25 years could still understand what the volume of a cylinder is, I expect all of you to know it too. So you could call her up and thank her, because she's the one making you all know this. So for this situation, pressure is force divided by area. Now the force is mass times gravity. That thing is just getting pulled down. The area, well, I didn't give you the area of the cylinder, but I did give you the volume. Volume, you could think of also as base times height. That base is the area of the cylinder. So we can write area times height. So area is volume divided by height, and 1 over area is height divided by volume. So mgh divided by volume. And yeah, and so I now have everything that I need. No, I don't. M mass over volume is density. So that means mass is rho times volume. So mass, density times volume times height divided by volume. And so those volumes actually cancel out. And I forgot my G. So it is rho GH is that pressure. So 1,000 times 10 times 2. Or 20,000 newtons per square meter. And that's the pressure. And one of the things that
What was the big H for?
the big H
Under area? They're not A.
right here,
No, on the left hand. What is it? Oh, that's the A.
that's an A. Yes. But the one thing that we notice from this equation there is no mention of volume in the pressure equation of this particular form. Now, granted, we did start with it, but with a simple substitution, volume was eliminated. This is volume independent. It is only depth dependent. So all that mattered was not the geometric shape of the object. It could have been a sphere, or well, not a sphere. Could have been a cylinder, could have been a rectangular object, could have been a cube. All that matters is the height. So if you had a cylinder and the pressure at the bottom of that cylinder is known, let's say that P was 1 atmosphere, and you had a cone if both points are at the same depth, the pressure is equal. So if the pressure at the bottom of a 1 meter high cylinder is 1 atmosphere, then the depth, or then the pressure at the base of a 1 meter high cone is also 1 atmosphere. The pressure on this side of the room at the floor is the same as the pressure on that side of the room on the floor. And what we're going to start talking about is the idea of Pascal's principle points at the same elevation have the same pressure. Now it has to be, they have to be like either connected systems, or there has to be like uniform systems. In both of these, they both are water. And one of the things about Pascal's principle that's kind of interesting is that if you had like a big tub of water, and that was at 1 meter and this was at 1 meter, pressure 1 is equal to pressure 2. That just makes sense. It's in the same bowl. If the pressure over here was greater than the pressure over there, the fluid would just, some of the fluid would go over there and then it would even out eventually anyway. You could also do this. The pressure at that part and the pressure at that part, if they're both 1 meter underwater, the pressure at 1 is again equal to the pressure at 2, regardless of the geometry that occurs between the 2 points. If both have 1 meter of fluid above it, then it's the same pressure. And you can even say that the pressure at the top, they're at the same level of fluid, then the pressure at 3 is equal to the pressure at 4. Now, Pascal's principle we take advantage of every day. The most commonly used problem that I use are the hydraulic lift. The hydraulic lift, obviously everyone has either had their oil changed or are at a place where they're changing oil, and they take the car and they put it on that lift and they hit the button, and then this big metal cylinder just comes up out of the ground and lifts the car up so the mechanic can work on it. They take advantage of Pascal's principle. On one hand, you have your car. There's my car. And the mass of the car is 2,000 kilograms. And it's sitting on a plate of an area, let's say, is 10 square meters. And it is hooked up to it's basically sitting on a pile of hydraulic fluid. Hydraulic fluid is fluid that you can't compress easily. And on the other side, there is basically there's a piston pushing down on a cylinder of this fluid which is attached to this. And the area of that piston is 0.1 square meter. The question is, how much mass rests on the piston so that it balances the car? Well, they're at the same level of fluid. They're both at the same heights. So the pressure at the piston is the same as the pressure underneath the car. Now, the pressure underneath the car is the force of the car divided by the area of the car plate, and the pressure of the piston is the force of the piston over the area of the piston plate. The force of the piston is mass of the piston times gravity. The force of the car, mass of the car times gravity over area of the car. Gravities cancel, and the mass of the piston is equal to area over area times mass of the car. So area of the piston, 0.1, area of the car, 10, mass of the car, 2,000. 0.1 over 10 is 1 over 100. 2,000 divided by 100 is 20. So a 20 kilogram object sitting on the plate on the left is capable of balancing a 2,000 kilogram car on the right. And all this takes advantage of is the Pascal principle. We won't do a problem, but it's another thing. You may have heard of something called the master cylinder. Master cylinders are parts of the car where there are all these hoses of incompressible fluids you have a brake on one side and the brake pads on the other. You push down on the brake, the area of the brake is small compared to the area of the brake pad. And what did we see when a certain amount of force is put on a small area? A much larger force is put on the bigger area. So this is why when you press on the brakes, you're able to stop your own car, which is a very big object. Because that little amount of force from your foot on the brake, on the brake pedal, produces a much larger force on the brake pads, which are clamping down on the rotors. And this is one of the reasons why cars do what they do. This is why the master cylinder is so important. If you lose that fluid pressure, suddenly your car just becomes a big brick and you're unable to stop it, which is a bad thing. So Pascal's principle is very, very useful. Couple of equations that we need to cover, and then we can do more interesting stuff next week, is the idea of equation of continuity. And of course, what's going to happen is tomorrow we're doing our normal Bishop Hall tutorial, 1 o'clock. We'll just talk about the homework for an hour, and it'll be recorded, of course. The equation of continuity explains not explains garden hose behavior. If I had a running garden hose right here, I could probably shoot someone who's very close to the podium. But let's say someone was talking over there and I needed to shoot them with the same hose. How do I get the water to shoot out farther? Put your thumb over the hose, right? Yeah. So the equation of continuity is this. A1V1 is equal to A2V2. If you have fluid that's passing through a particular area and it goes through a part of the pipe which is at a smaller area, that volume, or the new velocity, is A1 V1 over A2. And V is velocity, yes. So let's say for a second that V1 is equal to 2 meters per second. And you cover half of the hose. You cover half of the hose, V2 is equal to A1 V1 over A1 divided by 2. So if you cover half of the hose, the new area, A2, is half that of A1. So the new velocity of water coming out of that hose is twice as much as it was originally. And so that is the equation of continuity. I call it, well, another thing that I call it is the conservation of flow. If you've got 1 gallon per second going into that hose, a gallon per second's got to come out. It's just the water can't go anywhere else. I mean, it's not magically disappearing, so 1 gallon coming in is a gallon coming out. Also, area times velocity. Area is meters squared. Velocity is meters per second. So that's cubic meters per second. And so sometimes this is called the flow rate. It lets you know the volume that's coming out of the pipe every second. So flow times time is volume. Flow is in meters cubed per second. Time is in seconds. That leaves you with meters cubed. Some other topics that we need to just, I skipped over at the wrong time. Let's get back to I know exactly what I need to do. For this equation, pressure is rho GH. That's the pressure at the base of a column of fluid. So if we had, just as a rule of thumb, one example that we're going to go over in on Tuesday really illustrates the point of who I am. And one of the things that I used to do in high school and college, used to scuba dive a lot. And the rule of thumb was for every 10 meters of depth, your total pressure increases by 1 atmosphere. And this brings up the whole idea of total pressure. If you are, let's say there's the surface of the ocean, and this is you scuba diving. If that height is 10 meters, the pressure due to the water is 1 atmosphere. So if you're at the bottom of a 10-meter pool, the pressure of the water on you is 1 atmosphere. Now, just like those kids piling up on top of me, you have to count all the kids. When you're a scuba diver, you also have to count the pressure of the air pushing down on the water. So when you're at 10 meters underneath the surface, the total pressure is atmospheric pressure plus pressure due to water. So this becomes 1 atmosphere plus 1 atmosphere or 2 atmospheres. So if you're 10 meters underwater, your total pressure is 2. So at surface, it's 1, 10 meters, it's 2, 20 meters, it's 3, 30 meters, which is about as far as you really need to go underwater without special equipment. So you have to understand total pressure. And this brings up the idea of gauge pressure. When you have, you're inflating your tires, so you're at the gas station, and you put your little gauge on top, that gauge is reading the pressure on top of atmospheric pressure, the additional pressure. In order for your tires to do what they're meant to do, they have to have a pressure greater than atmospheric pressure, otherwise they would just collapse. Total pressure is 1 atmosphere plus gauge pressure. If your pressure reader says 2 atmospheres, the total pressure in the tire is 3, because it's got to keep out the atmospheric pressure and then a little bit extra so the tire doesn't compress. So understand the difference between total pressure and gauge pressure, which will be used on the problem set. So that should have been mentioned. I should have stopped and mentioned it. It would fit into the lecture, probably right here is where we should have gone over gauge pressure and stuff like that. But the 2 biggest things, total pressure, you got to add 1 atmosphere for atmosphere. Gauge pressure is pressure on top of atmospheric. And rule of thumb, 10 meters of depth is 1 additional atmosphere. The last thing that we'll briefly touch on, we'll cover more about it tomorrow, but I got to get it out there, is just as Dr. Eschenberg has a favorite equation and a second favorite equation, some may ask, what is his least favorite equation? Glad you asked. It's Bernoulli's equation. Oh my goodness. Bernoulli's equation is an equation used most often. The classic Bernoulli's equation problem is you have a pipe it goes up a particular height. It has a pressure and a velocity. It has a pressure and a velocity up here. What are the pressures and velocity of the fluid as it goes up the pipe and as it comes down the pipe? All that fun stuff. That's Bernoulli's equation. And there is an equation that does this. P1 plus rho g H1 plus 1/2 rho V1 squared equals P2. Oh my goodness, this is why I hate it oh so very much, because it just goes on forever. And that's the equation. There is a pressure contribution from just the pressure of the fluid. Then there is pressure due to height. And there is pressure due to velocity. So pressure of the fluid has some basic things. This is the pressure that you can read. There are contributions made by the fluid in terms of its height and its velocity. Yes?
What's the subscript on the P on that equation? Like where you drew that?
Here and there?
No, above.
Oh, there. That's a P1 comma. Thank you. So, given all of these conditions, what's this? When you see something like this, you guys really should be excited because it's a plug-in chugger's dream. You just have to do this. As an example, let's say you had, oh, and this is the danger part of this whole thing. The velocity in the pipe is 20 meters per second. The pressure at the base is 1 atmosphere. No, I take it back. It's going to be 10 atmospheres. I need to get the math to work. H is 30 meters. What is the velocity at the top and what is the pressure at the top if I said what's the velocity at the top and what's the pressure at the top if that's genius. Area at the bottom is 0.1 square meter and the area at the top is, what would be a good thing to keep it from exploding? 0.08 meters squared. So we have a pipe that slightly decreases. The question is, what is the velocity and the pressure at the top of the pipe? How you do this is its equation of continuity followed by Bernoulli's equation. Because in Bernoulli's equation, we don't know what the velocity is for 2, and we don't know the pressure at 2, so we can't really use the Bernoulli's equation just yet. So we use the equation of continuity first to find V2. So A1 V1 is equal to A2 V2. And V2 is A1 V1 over A2. A1 is 0.1, A2 is 0.08, V1 is 20. Now, truth be told, you don't have to convert these to meters per second, or I'm sorry, you don't have to convert the areas to square meters, because you're dividing one by the other. As long as the units agree with each other, should be fine. And the answer is 25 meters per second. So the pipe shows, because the area gets a little bit more narrow, the velocity of the fluid at the top of the pipe is greater. Now comes the determination of pressure. P1 plus rho G H1 plus 1/2 rho V1 squared equals P2 plus rho G H2 plus 1/2 rho V2 squared. Now the only unknown is P2. How these problems are typically set up is that I just give you the height difference. And what I typically do is I say the lowest point is 0, so that means H1 is 0, and I don't have to worry about that. Once again, my favorite number is 0 because it just takes stuff out. Another question no one even bothered to ask: what fluid's flowing through this pipe? Let's just make it water. So the density of water is 1,000 kilograms per cubic meter. Once we're done with determining pressure, we'll leave.
Why did that cancel? Or why is it 0? You made it 0?
I made it 0 because I declared that level to be 0. All that's really important is the height difference. All that matters is the height difference. So if I say one is 0, the other one is 30. I'm looking for P2, so P1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared minus rho GH2 is equal to P2. Now this is where we have to come to a very critical velociraptor pit, and then I go, don't fall in the pit. This is how you avoid falling in the pit. You've got to ask yourself, what unit am I asking for? Am I asking for the pressure in newtons per meter squared, or am I asking for atmospheres? You've got to know what this is, because I always ask problems like this with this trap just sitting inside waiting. I gave you pressure at the base in atmospheres. 10 atmospheres. When you look at rho V squared and what its units are, that's kilograms per cubic meter. Velocity is in meters squared per second squared. I'm going to cancel only one of the meters, and that leaves me with kilograms meters second squared times 1 over meter squared. This becomes newtons per meter squared. Rho V squared and rho GH, they all produce pressures that are expressed in terms of newtons per meter squared. I intentionally set it up so that the units were different. These are in newtons per meter squared. I gave you P1 in atmospheres. So you're gonna have to do a conversion. Let's say I asked, you decide, should the answer be in atmospheres or newtons per meter squared? Pick. Don't look at your notes, just say it. Guess, it's like flipping a coin. Atmospheres, great, atmospheres. So what that means is, if she wants the answer in atmospheres, that 1/2 rho V1 squared minus 1/2 rho V2 squared minus rho GH2, they must all be divided by 1.013 times 10 to the 5th newtons per meter squared per atmosphere. So you're going to have to take those 3 segments and divide it by 1.013 times 10 to the 5th. It wasn't that hard. I'm being mean. Okay. So there you go. Now, really all I'm going to say is this. You guys love to plug and chug. Here's a whole bunch of variables that you know everything about. Go to town. And I'll leave it to you to plug in those values. And then you'll get an answer for P2, and that answer will be in atmospheres. Because that's already in atmospheres. This is the conversion for those 3 to go into atmospheres. And so now you're good to go. That said, tests are up front. They'll be in the filing cabinet sometime this afternoon. Tutorial tomorrow at 1. Thank you.